Okay, so we'll go ahead and get started at the moment. Okay, previously, last week, what did we do? We talked about probability interpretation of the, right. So we talked about, last week we laid the foundation, and the week before we laid the foundation about whether or not particles can be treated as waves, because light can be treated as particles and waves. So this whole wavical idea, we wanted to apply this to particles. And we saw that this idea of a standing wave, a stationary state for an electron and an atom, was more than just a convenient matter for solving certain characteristics of the atom, the finite energy transitions and so forth. So, what was his name? De Broglie came along and gave us this interpretation, the momentum of a wave for an electron that's in a stationary state, and gave us this situation that looked like a standing wave pattern in standing wave pattern for an electron that's in an atom in some given state. So it's a modification of the Bohr atom, a significant one, because it went further in explicitly stating that the electron not only was in this stationary state, but it's a standing wave pattern in this stationary state, similar to the classical concepts. And so we then took this and applied it as a general thought on Friday. We talked about the probability characteristics for something that's in a wave state. We also introduced a type of notation that we won't explore thoroughly in this course, but you will see in subsequent quantum mechanics courses and in other advanced mathematics, the Broadcat notation. So I think we talked about the Heisenberg Uncertainty Principle. I put a definition up for you. I just want to make sure I gave you guys Heisenberg Uncertainty Principle. No erasers. Does that look familiar? Is that I feel like I did write that up on the board. Okay. So I'm assuming everybody remembers seeing this. And there's another version of it. That's right. That's right. Okay. So, well, let me go ahead and do this. Let's go and make this an official definition then. this down a little bit. Sigma x, sigma px greater than or equal to h bar over 2. All right, so setting the scene. Now we've got Bohr's model. It's been around for about a decade. And then de Broglie says there's something squishy about this. Let's see here. So he says there's something squishy about this whole Bohr model of the atom. Sure, and we talked about the weaknesses in there, and de Broglie said, well, let's talk about the electron as waves, as some kind of wave format. And we go, oh, that kind of makes sense. So now, where it's about 1824, 1924, 1925, and Joe Heisenberg, I don't remember his first name, Mr. Heisenberg postulates that there is a limit to being able to make a measurement, an observation. In other words, perform an operation on a system in order to do that measurement, an operator. And that limitation has to do with either position or the momentum. So if you try to measure the position and the momentum simultaneously, you have to sacrifice your understanding of one in order to have good understanding of the other. You can't, and this is a statement about the uncertainty or the wellness at which you are able to make your measurement, not the actual measurement itself. This is a limitation that says it's got to be greater than, when you multiply these two uncertainties together, it's greater than h bar over 2. There's a version that applies to energy and time as well. These two operators are not fully independent. They can't be treated completely independently. And so we have the Heisenberg Uncertainty Principle that comes into play. Let's do an example. So we have electrons in the nucleus. The question is, can we estimate what the kinetic energy is of an electron that's confined in the atomic nucleus? In other words, is it going to be sensible? Is this going to make sense? We're going to use the uncertainty principle, and we're going to use an estimate of about 1.0 times 10 to the minus 14 meters as the size of the nucleus. So let's just take a rough estimate. Let's see here. So we'll just take the estimate of the nucleus uncertainty to be half the size of the nucleus. We modify the position momentum vector, or position momentum uncertainty. This must be greater than or equal to h bar by 2 delta x, or sigma x. H bar, what was that? Let's read that number, 6.626. 1.055. Let's see, joules. I want this one in 6.582 times 10 minus 16. Was it? Divided by 2 times 0.5 times 10 to the minus 14 meters. The uncertainty conversion is not obvious here. Oh, because we're doing the C. That's meters per second. Okay. So this will be, where's my calculator? EV per meter per second, which is kind of a weird, odd unit. And since we're going to be going to kinetic energy, we can go ahead and make a conversion and have it reported in factors of C. So let's take this, convert it, 1. 3, 2.99. 10 to the 8th meters per second from 1C. This works out to be 2.0 times 10 to the minus 10 to the positive 7. So far, so good. So it's a pretty big uncertainty there. Then we use you'll notice that this value here is 20 mega electron volts per C. When you work out those decimal places. So that before we even go any further to talk about what the actual kinetic energy is, the question is, well, something to think about is, look at this number. This is the uncertainty in the momentum in the x direction. It has to be greater than or equal to 20 MeV per C. So that's a huge range. This is a plus or minus, right? That's what the uncertainty is. So whatever the energy is, we only know it as well within 20 MeV per C. It's kind of a big deal. So let's assume that's 20 MeV per C. So mass of the electron, 0.511, 0.511 MeV per C squared times C squared squared. It's about 400 MeV. You see that the energy of the electron just gobbles up the mass of the electron, the mass rest energy. K is equal to E minus 20 MeV minus 0.511 MeV C squared, C squared. Dots. What does this mean? Let's interpret our numbers. Remember, we're not just doing math. We're understanding the concepts that are associated here. What does this mean? 19.5 MeV for the kinetic energy of the electron. Does it seem like a reasonable number? Is that a reasonable kinetic energy? What is the energy, say, of red light? Well, that's going to be h times the wavelength, h frequency. Let's do that real quick over here. Context. You guys see that okay? Find the energy of let's not say red light. We saw violet in the excitation light from the mercury. So let's say violet light, getting close to that UV range. Well, energy of violet is going to be given by, remember what it's given by? What the equation is for energy of a electromagnetic wave, energy of any wave, technically. Come on.
So, or the product of the Planck constant and the frequency.
HF, exactly. And we know that light travels at wavelength times frequency, so we can write this as H C over lambda. What's the wavelength of this light? Let's find out. Wavelength of violet light. Oops.
300.
Okay, 300. Nanometers. Okay. 6.626 times 10 to the minus 34 joules seconds times 2.98 times 10 to the minus positive 8, I always get that backwards, meters per second, over lambda, which is 300 times 10 to the minus 9 meters. Seconds cancel out with seconds, meters cancel out with meters. This is in joules. We need to have that in EV. So 1.602 times 10 to the minus 19 joules for 1 electron volt gives us a grand total of 4.13 electron volts. Is that all in the picture there? Which one's going to have more energy, red light or violet light? Agreed. Because violet's going to have a longer wavelength, which make this number bigger, which means the energy is going to be lower. So we're already looking at the upper end of the visible spectrum. And we were talking about mercury, which has a pretty good sized nucleus, and even then, still on the order of 10 to the minus 14. So even if we assume that we were wrong to within half the nucleus, that's a that's pretty good size. If we're not even sure to within half the nucleus, and we still come up with this energy that is 19 times 10 to the 6th more energetic. Oh, let's say this, not 19 more, but 4 times 10 to the 6th more energetic than the energy that's associated with the electron that's transitioning to give the energy. Would it be reasonable to expect? What does that tell us about the likelihood that the electron stays in the nucleus?
It's pretty low. It will eventually go down to look at less excited state or whatever accessible to it.
Agreed. So it just seems like it's unlikely for it to be confined within the nucleus, because it would be required to have such energy as this that doesn't fit with the experimental information or even the logical situation. So that's the uncertainty principle. Any questions on that?